Hey guys, here's number 2. Okay, so yesterday we were talking about thermodynamics, enthalpy of a system, and we finished up with the exothermic and endothermic change. So today we're going to get into enthalpy, but I want to go a little bit deeper into this endothermic and exothermic. So if you remember from the last unit, here are the two examples of the activation energy of a reaction, right? And we talked about the difference between exothermic and endothermic. Well, the one on the left here represents a reaction that is exothermic. So I'm going to go ahead and put that right here. Exothermic. So a couple of things I want you guys to understand. So when you're talking about the types of reactions, the exothermic and the endothermic, right? We're talking about the overall energy of the system and the surroundings. So remember that here we have our reactants. Okay, and here we have our products. So remember that in an exothermic reaction, the system is actually losing energy into the surroundings. So the system should have less energy after the reaction in the products than it does when it begins. So if you take a look at the energy of the starting, which is the reactants here, you're going to notice that it has less energy at the products than it does at the reactants. Now, the energy we're talking about here is the potential energy. But the potential energy is the energy of the system, and the kinetic energy, which I'm going to abbreviate here as kinetic energy, is the energy of the surroundings. So what we have is, as the kinetic energy increases in the surroundings, we begin to see an increase in temperature. So here you have higher kinetic energy in the surroundings, which means you have a higher temp. So when we have an exothermic reaction, we see an increase in temperature in the surroundings. In the system, you have lower, or you have higher potential energy and lower potential energy. And that makes sense because in an exothermic reaction, the system is giving away energy, which is where we get that the energy here for an exothermic reaction is going to be negative because the system is actually losing energy. If we go to the other side and we take a look at an endothermic reaction, right, we see that the energy of the products is actually higher than the energy of the reactants, right? So here are our reactants. Okay, so the energy of the products, if you look here, is actually higher. Now, this energy is the potential energy. Now, what we see in the surroundings is we see a decrease in kinetic energy, right? We see a decrease in kinetic energy. So in the surroundings, we see a decrease in the temperature. So the potential energy is the energy of the system, and the kinetic energy is what we perceive, which is the energy of the surroundings. So we see in the surroundings of the system in an endothermic reaction, we see or observe a drop in temperature, right? But the system is actually absorbing energy or potential energy, which is why you see that the energy of the products here is higher than the energy of the reactants here. So these two activation graphs show you the difference between between exothermic and endothermic reactions. So in this case, the system gains energy, and in this case, the system loses energy. What we perceive is the stuff in the surroundings, right? That's where we see the increase in temperature and the increase in kinetic energy. We see that in the surroundings. Now, think about this like a magnet, right? In an exothermic reaction, right, these magnets here that we see are racing towards each other because they have that really strong attractive force. When they snap together, right, that snap releases that energy into the environment, into the surroundings, and we perceive that as an exothermic reaction, right? Now, these types of reactions, because they need no assistance, they have an attractive force, right? We call these spontaneous. right? These call these spontaneous. What that means is they happen on their own. On their own. With no outside energy, right? So you have these two magnets, they're racing towards one another because they have that attractive force. And then when they snap together, the energy released is considered exothermic. So that's kind of an analogy of what we see here with an exothermic reaction. Now, in an endothermic reaction, you have magnets that are already together, right? In order to pull them apart, you need to introduce some outside energy or outside force into the system to pull these magnets apart. In this case, that'd be like your hands. You put your hands on the magnets and then you physically begin to pull them apart. The energy that you're introducing into the magnets is forcing them apart. Therefore, you're introducing energy from the outside into the system. Okay? We call this type of reaction non-spontaneous. Non-spontaneous reaction. This means that it needs assistance. Or it needs outside energy. Going in. Okay? So, this is the fundamental difference between an exothermic and an endothermic system, right? Now, when we're talking about the total energy of a system, okay, we call that enthalpy. Okay? The enthalpy of the system. Now, enthalpy is represented by the letter H. This is enthalpy. Okay? Now, the enthalpy of the system can be defined again as the total energy of the system. When the energy or the enthalpy of a system changes, then we call that a change in enthalpy. Remember that delta represents change. So when we have an enthalpy of the system, then what we're talking about is we're having the change in enthalpy, which is the final enthalpy minus the initial enthalpy. Okay, that's what we're talking about. So when we're talking about final initial in terms of a chemical reaction, remember that a chemical reaction proceeds from reactants to products. Right? It goes from reactants to products. So if we're going to represent the enthalpy of a system in terms of a chemical reaction, then we're going to rewrite the formula as the change in enthalpy of a system is equal to the enthalpy of the products minus the enthalpy of the reactants. Okay, and this is our formula for the change in enthalpy. Now, enthalpy, okay, is a state function. Now, what does it mean for enthalpy to be a state function? That means that a state function, like the change in temperature, has to do with what's happening at that moment, right? It doesn't matter what caused the change. It doesn't matter what energy was added to cause the change. What it matters is that the energy is changing. So just like temperature, right, I'm going to put this in. Just like temperature is a state function, temperature final minus temperature initial, all right? Enthalpy can be measured exactly the same way. And the change of enthalpy is going to be the reactants minus the products. So it's an absolute value that has to do with the changes in the system at that moment. Everything else is irrelevant, okay? Now, when we're talking in terms of exothermic and endothermic, remember that energy or heat is equal to the energy, right? Because we said that most of the time, heat is a byproduct of energy, right? So when we're talking in terms of exothermic and endothermic, then that also relates to the enthalpy of the system. So if we have delta H as positive, then we can say that that is an exothermic reaction or change, right? An exothermic change. If, however, your enthalpy of the system after you do products minus reactants ends up being in the, sorry guys, made a mistake here. This is supposed to be negative. If the system has a positive value, then this represents an endothermic reaction or endothermic change, right? This also relates to the energy or the heat. Remember from before, all right? So when we're talking about enthalpy, if your enthalpy is positive, you have endothermic. If your enthalpy is negative, then you have your exothermic, okay? Going out to the system. So in short, the change in enthalpy can be construed as the change of heat transferring from one system to the other. Now, remember that energy in the universe is constant. Energy does not create or cannot be created or destroyed, kind of like the law of conservation of mass. We have the law of the conservation of energy. Energy can only be transformed, right? Because we can measure how it's being changed. Now, how we measure that is by a process called calorimetry. Calorimetry is how we measure how energy is transformed, right? So let's take a look at this example question right here. Okay, we have a chemical reaction happening between hydrochloric acid, sodium hydroxide. A student places 50 mLs of 1 molar HCl into a coffee cup calorimeter. Now, this is a very simple experiment, okay? You're going to have a coffee cup, usually styrofoam, placed inside of a larger coffee cup, also styrofoam, to create an insulated barrier, okay? So this is the basic premise of a coffee cup calorimeter. Now, what happens is this makes a semi-closed system, okay? And then the reaction happens inside here. All right. Now, it says a student placed 50 mLs of 1 molar hydrochloric acid into a coffee cup calorimeter and carefully measured its temperature at 25 degrees Celsius. So let's go ahead and add our hydrochloric acid. So I'm going to go ahead and fill it up here. 50 mLs of hydrochloric acid. Okay. Now, at this point, temperature equals 25 degrees Celsius. The mixture was quickly stirred. Oh, and then added was 50 mLs of 1 molar. So then to this solution, was added 50 mLs of NaOH. So this is my NaOH. This is my HCl. Okay. The NaOH was also at 25.5, not 0.0. Okay, and was quickly stirred. Now, the change in temperature went from 25.5 to 32.4. So I'm going to go ahead and do 32.4 degrees Celsius minus 25.5 degrees Celsius, okay, to get a change in temperature of 6.9 degrees Celsius. Okay, 6.9 degrees Celsius. So now we know how much the temperature changed. Okay, now the question is asking, what is the heat of reaction in calories and joules? So here we see that we're looking for calories and joules, and specifically what's looking for the heat of reaction. Okay, now, blah, blah, blah. All right, so how do we figure this out? Well, remember from before that heat is equal to the specific heat times the mass times the change in temperature. All right, so we have the information. Now, what we don't have is the specific heat, but actually, if you look, it tells you right here, the specific heat of the solutions is 1.0 calories per gram Celsius, right? And the density of each solution was 1.00 grams per mil, which will help us determine the mass. Okay, right, because we're adding milliliters. Okay, now in this system, right, in this coffee cup calorimeter, because the calorimeter is how you do calorimetry, which is how we measure the amount of energy that is absorbed by a system, okay, we have to combine the masses of both, right? Because inside here, we have this 50 mLs plus we have this 50 mLs. So the total volume that's been added here is 50 mLs. Sorry, for each one, right? So that gives us a total of 100 milliliters of both mixture. Okay, so there's our mixture. Now, if we multiply by the density, I know that the density according to this is 1.00 grams per mil. Okay. And if it's a 1, the mils cancel. And I'm left with a total mass of 100 grams mixture. Okay. Now, we've already calculated our temperature change, and then it says our specific heat is equal to 1.00 calories per grams degrees Celsius. If I multiply that by 100 grams, which is my mass, and I multiply that by the change in temperature, which is 6.9 degrees Celsius, here's what happens. I'm going to multiply these together. My grams cancel here. My Celsius cancel here. Okay. And if I multiply all these numbers together, I'm going to end up with 6.9 times 10 to the second calories, right? Because all my other units canceled. Now, we saw an increase in temperature. This increase in temperature here was an increase in the surroundings, right? So because we observed an increase in temperature of the surroundings, then this value has to be negative, because that means that our heat is negative, which makes it exothermic. Therefore, our value becomes negative 6.9 times 10 to the 2 calories, right? Now, the question also asked us to find it in moles. So if we do it in moles, right, remember, like I said before, that 1 calorie is equal to 4.184 moles, or joules, sorry. Therefore, negative 6.9 times 10 to the 2 calories times, I know that every 1 calorie is 4.184 joules, then is equal to negative 2.9 times 10 to the third joules. Now, what we take away from this problem is the way we measure, right? The way we measure the energy being transferred is through a process called calorimetry. Okay? Calorimetry is what we use to measure the changes in specific heat, transfer in a system. The instrument that we use, right? The instrument that we use to measure this is called the calorimeter. Okay. So the enthalpy of the system is measured as the total energy of a system when we have a transfer of energy within a system to the surroundings or vice versa. We measure that using calorimetry, and the instrument used in calorimetry is called the calorimeter. This is an example of a calorimetry problem, okay? And we'll go ahead and stop it there for today.